Alamo. Bessie is Bessie. Bishop here. Bishop is here. Bessie's here. Brad here. Cornell. Chestnut. Coolwood. Burlington. Gerard. Green. Kennedy. Leonard. Mohammed Boy is here. Spall is here. Solomon is here. Swissack. Okay, so we're going to continue our discussion on chapter 3. Oh, by the way, did I talk to you guys about testing your first test? No. Okay. So according to the syllabus, your first test should be next week. However, I'm going to put it up onto the other week, only because we're not finished with chapter 3 yet. I want to finish chapter 3 so that you can complete that assignment, turn it into me, and then I'll get it back to you so that you can have it to review for your test, right? So basically, I would say that your first test will be not next week Thursday, but the other Thursday, right? So, and I'm going to post an announcement about that as well. Okay, so again, a bit of a review. What we'll be talking about today is, well, to begin with, is the relationship between molecular formulas and empirical formulas, right? And I think we touched on the definitions earlier. So just to remind you, the molecular formula for a compound is a formula that gives the number of atoms of each element present per molecule. The empirical formula gives you the simplest ratio, or I should say simplest whole number ratio of the different elements, of the atoms of the elements present in a compound. So an example here is given. The empirical formula CH2 means that the molecular formula could be CH2, or it could be C2H4, could be C3H6, or it could be C4H8, right? Because each of these gives the number of atoms of each element present per molecule, but the CH2 gives you the ratio of carbon to hydrogen atoms present. All right. So how do we define the molecular formula? Well, if you know what the empirical formula is, then you should understand that the ratio between the molecular formula mass and the empirical formula mass would be an integer, right? And that integer you can use to multiply the empirical formula to get the molecular formula, right? So that's basically the relationship between the empirical formula and the molecular formula. It basically comes down to what we call the integral factor, all right? Okay, so just to give you an example, let me see if I can move this on. Okay, so this question says, the empirical formula of hydroquinone is C3H3O, and its molecular mass is 110 AMU. What is its molecular formula? So very simple. First thing I would do is try to find the empirical mass. We get that by adding up the molar masses or the atomic masses of each of the elements. Plus 3 times 1.008 AMU plus 16.00 AMU. And this is going to give 36.03 AMU. This is going to give 3.024 AMU. And this is still going to give 16.00 AMU. And then we do the addition. 6.03 plus 3.024 plus 16. So I got 55.05 AMU. And then we get the integral factor by dividing the molar mass by the empirical mass. And well, molecular mass, 110 divided by 55.05 AMU. So 110 divided by 5.05. And the answer I got when rounded off to two six figures would be 2.0, right? So basically, that would be the integral factor 2. So therefore, the molecular formula would be equal to C3H3O multiplied by 2, which is the same thing as C6H6O2. All right. Any questions? Any questions about this example? Yes, sir.
Below where you have the 55.05 AMU,
Mhm.
what is that section there?
You mean here?
Yes, sir.
Okay, so what I'm doing is calculating the integral factor by dividing the molar mass or the molecular mass, which is given,
Okay,
right, by the empirical mass, which you just calculated here.
okay.
And that gives you the integer, which you're going to use to multiply the empirical formula by to get the molecular formula. Right? Okay, any other questions? Any other questions? Okay, moving along. Okay, now here's something that I'm quite sure you did not meet in your previous chemistry experience. So I'm going to take some time talking about it. So you might be wondering, how do we get these percentages experimentally, right? Because you can't get them experimentally for a compound. What we're going to talk about is how we do so for an organic compound. Now, you may or may not know this, but the term organic in the context of chemistry basically means compounds containing carbon, right? So organic compounds are compounds of carbon. There are some exceptions to that, like carbonates, cyanides, and so on. But most other compounds that contain carbon, they are considered to be organic compounds. And most organic compounds contain carbon and hydrogen. And then you have a good number of them that contains oxygen. And then in addition to that, you may have other elements like nitrogen, halogens, sulfur, and so on, right? So when it comes to these compounds, there is a way of determining the percentages of each element present in that compound. And it's called combustion analysis, right? It's a form of elemental analysis, right? So as stated here, this method is used primarily for simple organic compounds that contain carbon, hydrogen, and oxygen. So the way this works is that you weigh the amount of that compound that you're analyzing, and then you burn it, right? And as you should know, whenever you burn any compound that is organic, the two major products would be carbon dioxide and water, right? If other elements are present, then you'll end up with some other products. But if the compound contains carbon, hydrogen, and oxygen, then you know that the products will be carbon dioxide and water. So what we do in this particular situation is that after the complete burning of the compound, we somehow trap the carbon dioxide and the water, and then we weigh those two substances, and then we work backwards to figure out the mass of carbon and hydrogen and oxygen that is present in the original compound that is burned. So that's what I've just described is an overview of how that is done. And the next slide gives a diagram, a schematic diagram of how this is done, right? So here we have 3 chambers, right? The first chamber will contain your sample. So in practice, what you do is you weigh your organic compound, you place it in this chamber, which is a furnace, right? You make sure that you have excess oxygen rushing in. And what this does is that it burns the compound, and as I said before, the products of the combustion of the organic compounds will be carbon dioxide and water. And those gases are led from here through this pipe into this chamber. Now, this chamber contains a compound, magnesium perchlorate. And if I remember correctly, there's another alternative compound that can be used. I don't remember what it is right now, but we're working with magnesium perchlorate here, right? The role of the magnesium perchlorate is to absorb the water that is produced as a result of the combustion of your organic compound, right? So again, in practice, what you do is before you start anything, you weigh the magnesium perchlorate initially, right? And then after it absorbs the water, you weigh it again. The difference between those two masses would be the mass of the water that it absorbs, right? So you have to ensure that you have enough magnesium perchlorate here to absorb all the water, right? Because the only thing you want to emerge from here now would be carbon dioxide. And that will be led into this chamber, which contains sodium hydroxide, right? And what will happen is that the sodium hydroxide will absorb the carbon dioxide. So again, just like you did in the previous chamber, you weigh the sodium hydroxide first. Then after the reaction is complete, you weigh it again. There'll be an increase in mass. That increase will be due to the absorbed carbon dioxide. So therefore, as a result, you can determine the mass of water that is absorbed here, the mass of carbon dioxide that is absorbed here, and then based on those masses, you can determine the mass of carbon and hydrogen and oxygen that is present in the original compound. All right, so this is just rehashing what I just said. Water is absorbed by the magnesium perchlorate, and carbon dioxide is absorbed by the sodium hydroxide. So this is just an example of how the analysis works for a simple organic compound like methanol. So basically you start off with your methanol. Of course, you'd have to wait, and then you make sure that there's an excess amount of oxygen that is reacting with the methanol as you're heating it. And then you're going to end up with your carbon dioxide and your water, but you still have some unreacted oxygen because of course it's an excess. And again, based on the masses of the carbon dioxide and water produced, you can determine basically the formula, the empirical formula of the original compound based on the masses of carbon and oxygen and hydrogen. All right. Okay, so here's an example. And since I'm going to need space, let me so here's an example of a combustion analysis question, right? A question based on the type of experiment I just showed you. And let me go, let's see if this works. Okay, so here's a question. Burning a 0.100 gram sample of a carbon, hydrogen, oxygen compound. So it tells you that the compound contains these three elements. In oxygen yields, and it gives you masses of carbon dioxide and water produced, right? And then it says a separate experiment gives the molecular mass as being 90 AMU. And they're asking for you to determine, firstly, the mass percent composition, B, the empirical formula, and C, the molecular formula, all right? So let me make this bigger. Okay, so okay, so remember now the compound contains carbon, hydrogen, and oxygen. Right? We don't know what the formula is, but we know that when this is burnt, you're going to get carbon dioxide and water, right? So if you determine the mass of carbon that is present in the carbon dioxide produced, then that will be the same as the mass of the carbon. If you determine the mass of hydrogen in the water that is produced, then you're going to basically assume that will be the mass of the hydrogen. Now, as far as the oxygen is concerned, right? The way you determine the oxygen is you add the masses of the carbon and hydrogen, and then you subtract that from the original mass of the compound, which is this right here. And that will give you the mass of the oxygen, right? So what I'm going to know is how you actually do that. So the first step is to determine the mass of the carbon. You're given 0.1953 grams of CO2, and you want to find out the mass of carbon in grams, in that mass of carbon dioxide. So we start off with the 0.1953 grams of carbon dioxide. And the first thing I would do is convert that to moles, where you're going to have 1 mole of CO2 down here. And down here, you have a molar mass, which if you add it up, will be equal to 44.6 0.01 grams of carbon dioxide. So that this would go with that as far as the units are concerned. And then the next conversion factor is where you convert the moles of carbon dioxide to moles of carbon, right? So how we do that? Well, it's based on the formula for carbon dioxide. The formula for carbon dioxide is CO2. So what that tells us is that for every 1 mole of carbon dioxide, there's 1 mole of carbon present. So we're gonna put 1 mole of CO2 down here and 1 mole of carbon above. Oops. 1 mole of carbon above, all right? So this unit will cancel with this unit. Then the next conversion factor is where we convert from moles of carbon to grams of carbon. And this is where the molar mass comes in. You consult the periodic table, and of course, you'll see that for carbon, the molar mass is 12.01 grams of carbon for every 1 mole of carbon. So that will go with that. And then you do the number crunching, and that will give you the mass of carbon in the carbon dioxide. So that's 0.1953 divided by 44.41 times 12.01. And then according to my calculation, again, please check to make sure I'm doing the right thing. But this is what I got. I got 0.0539. You have to round off to 4 digits, right? This is actually, hold on, no. 330 grams of carbon, all right? 0.5330 grams of carbon would be the mass of carbon that is in the mass of carbon dioxide obtained in the experiment, all right? Okay, so now that we have the mass of carbon, the next thing we need to do is find the mass of hydrogen. And we have to start off with, in order to do that, with the given mass of water, which is 0.1000 grams of H2O. And you're going to do something similar to what you did in this line right here. The first step of which is you need to determine moles of water, right? So you're going to have 1 mole of H2O, right? Divided by the molar mass, which if you add it up would be 18.02 grams of H2O, right? So that this goes with that. The next step is where we convert the moles of water to the moles of hydrogen. And let me just say here that over the years, this is something I've observed where students tend to make a mistake, all right? So please follow carefully. If you look at the formula for water, the formula for water is H2O, right? 2 hydrogens per molecule of water, right? So basically, in terms of the mole relationship, what that means is that for every 1 mole of water, there are 2 moles of hydrogen. And the way you represent that here is 1 mole of H2O will go down here, and 2 moles of hydrogen goes up top, all right? So this will cancel out with this, all right? And then the last step is similar to what we did before, where we convert the moles of hydrogen to grams. So that means we need a molar mass of hydrogen. So 1 mole of hydrogen will go down here, and the molar mass of hydrogen will go up top, which is 1.008 grams of hydrogen. And then we do the number crunching again, 0.1 divided by 18.02 times 2 times 1.008. And here is what I got. I got 0.01119 grams of hydrogen. Again, please check to make sure I'm on the right track, because I can be wrong sometimes. Okay. So far, excuse me, we have determined the masses of carbon and hydrogen. But remember, the compound contains carbon, hydrogen, and oxygen, right? So now we need to find the mass of oxygen. How do we find that? Let's go down here. The way we find that is that the mass of oxygen will be equal to the mass of the compound, mass of the original compound, minus the sum of the masses of carbon and hydrogen, right? So The mass of the compound was 0.1000, 0.1000 grams, minus these two masses, which would be 0.05330 grams plus 0.01119 grams. And let's see what that gives. 0.0, I'm gonna work on what's within the parentheses first, so 0.00. No, 0.05330 plus 0.01119. And then I'm going to subtract that from 0.1. Okay, so the answer I got is 0.03551 grams, all right? So that will be the mass of oxygen. So now that we have the masses of those three elements, we can now move on to determining the percentage of each element present in a compound. Okay, so is it okay for me to erase some of this? All right, so let me just erase this here. I'm just partially erasing because I'm gonna need some of the information that I have here. Yeah. So this is, oops. So these are the numbers we're going to use. This would be the mass of the carbon. This would be the mass of the hydrogen. And this here is the mass of the oxygen, right? So the A part of the question is asking for the percentage of each element. So in the case of carbon, that would be equal to 0.05330 grams divided by the original mass, which is 0.1000 grams, times 100%. And from the look of things, let me see here. That would be 53.30%. In the case of hydrogen, percent of hydrogen, that would be 0.01119 grams divided by 0.1000 grams times 100%. And this would be equal to 11.19%. And then finally, in the case of oxygen, the mass is 0.30355 grams divided by 0.1000 grams times 100%. And that will be equal to 35.51%. And that's it as far as the A part. And you can check to make sure that they add up to 100%, which I can tell they'll add up to, if not exactly 100%, almost 100%. All right. Okay. Any question about the answer to the A part? Any questions? Any questions? No questions? All right. Let me know when you're through writing down. In the meantime, let me see who came in late. Cordial? Chestnut?
You just be here in a second.
Okay. Colwood? Erlinson?
Here.
Gerard? Green? Kennedy? Leonard?
Here.
And Swista? Okay, finished? All right, so let me. So that was the A part. Now the B part is asking for the empirical formula. So we're gonna need the information from the B part. I shouldn't have erased it. So you guys are without help me. But basically, we're gonna do something similar to what we did last class, right? The bar table. Okay, now I need your help. Okay, what were the percentages for carbon, hydrogen, and oxygen that we determined from the A part? Carbon was 53.30. What about hydrogen? Was 11.19 grams, and oxygen was 35 point something. 5.1? Okay, I'll take your word for it. Okay, so if you remember, if you're given percentage values, then you assume 100% of the substance, which means that the percentages would be equivalent to the mass in grams of each element present. So let's see if you remember what we did the last time. What's the next step? Now that we have the masses, what's the next step? We divide by what? Not yet. Before that, we find the moles. 53.30 grams of carbon. To convert that to moles, we multiply by 1 mole over 12.01 grams. In the case of hydrogen, it's 11.19 grams multiplied by 1 mole divided by 1.008 grams. And then in the case of oxygen, 35.51 grams multiplied by 1 mole over 16.00 grams. Okay, so let's see what we get in each case. 53.30 divided by 12.01. And according to my calculation, I got 4.438 moles, all right? In the case of hydrogen, 11.19 divided by 1.008, I got 11.10. That's what I got, moles. And in the case of oxygen, 35.51 divided by 16, and I got, in that case, 4 sig figs again, 2.219 moles. All right, okay. So these are the moles. So what's the next step? What you said, Mr. Erlandson, what's the next step? Divide by the lowest number of moles, which would be the 2.219 moles. So this would automatically be 1. This would be 4.438 moles divided by 2.219 moles. And this would be 11.10 moles divided by 2.219 moles, right? So let's see what these gives. 4.438 divided by 2.219. Okay, so this gives exactly 2, right? And then 11.10 divided by 2.219. And this gives, well, what I have on my calculator is 5.002. So that would be effectively 5, right? So therefore, the empirical formula for this compound will be C2H5O. All right, and that's it. That's where you get that the answer to that question. All right. Okay. Any questions about this? Any questions? Any questions? Any questions out there in Zoom? Okay, so again, I need to erase everything here. Okay, so the C part is asking for the molecular formula for the compound. Now, they gave us the molecular mass, right? So how would that help us to determine the molecular formula? What would you do? They gave us the molecular mass. We have the empirical formula. The question is asking for the molecular formula. So how would you go about determining that? Huh? Remember what we did just before, at the beginning of this, well, yeah, very first topic we discussed in today's class. Okay, so how would you do that?
By molecular formula aspect.
Okay, so hold on a second. So we know that the molar mass is 90 AMU, right? So how will you find the empirical formula? Yeah, you add up the atomic masses. Let me do a quick calculation here. 12.01 times 2 plus 5 times 1.008 plus 16. Okay, so according to my quick calculation here, the empirical mass is equal to 45.06 AMU, right? So that would go down here, 45.06 AMU. And from the look of things, this would be approximately equal to 2. So what's the next step? How do we get the molecular formula?
To by the subscripts word.
So the final answer is going to be C for H10O2. And that's how that is done. All right. So this is a typical combustion analysis question. And I would say 90% sure that a question like this will come on your first test. How is that for him? All right. Any questions about this? Any questions? Any questions? Yes, sir.
How do you get the 45.06?
You just simply add up the atomic masses of the elements according to this formula.
Oh,
Right. All right. Okay, so let me go back to the PowerPoint. Okay, so again, this is a bit of review. I'm just going to go through it rather quickly. We all know what equations represent. Equations is a shorthand way of basically describing what happens in a chemical reaction. It involves the symbols for the substances involved as reactants and products. The reactants will be on the left side, the products will be on the right side. And you may get some additional information like state symbols, S for solid, L for liquid, G for gas, and AQ for aqueous solutions. You may see some additional symbols like a triangle, which represents that you heated the reactants to cause the reaction to go. In some cases, you might even get more specific information in terms of data for temperature, pressure, whether or not the catalyst is added, and so on, right? Of course, we all know the balance equation, right? The cardinal rule for balancing equations is to ensure that the number of atoms of each element on either side are equal, right? That falls in line with the conservation of mass law, right? Basically, what that law says is no atoms or matter is not created or destroyed when you have a reaction taking place. And the reason why that is because the atoms themselves are not created or destroyed, right? So when you're balancing equations, the only changes you can make to balance an equation which is not balanced to begin with are changes to the coefficients. You cannot change anything else. You cannot change the number of atoms. You cannot change subscripts. You cannot just add another atom on one side or the other. Basically, you have to make changes to the coefficients. So, what I just said basically is what this is all about. So let me just move on to these examples. So how would you balance the first equation?
Put a 2 in front of the product and then put a 3 in front of the O on the reactant side and then a 2 in front of the, or 4 in front of the FP.
Exactly, very good. Okay, any questions about that one? Any questions? What about the next one? Where do you here?
It's on the H2.
Okay. So that should be 1, 2.
Sorry, there should the.
1, 2 should be here, right?
Yeah, sorry.
And I think that's it. Okay, what about this one? The last one?
Need a 3 in front of the H.
Oh, you mean here?
Yes.
Okay, sodium cyanide. Okay. Okay, so, that's it as far as balancing equations are concerned. Oh, sorry, yeah.
On that second one, isn't there 7 oxygens? Or,
Oh, you're right, hold on. 2, 2, 6, 3. Oh, so this is all right. So what do we put there? How do we balance oxygens? We have 4 plus 3, 7. My ideas? I should know. We should know. Who else was in my class then? You guys back there should know. How would you balance oxygen in this situation? You have a total of 7 oxygens here, and on the left side, you have 2 oxygens. How do you get the 2 equals to the 7 or the 7 equals to the 2?
Right.
Multiply by a fraction, what would that fraction be? What would you multiply this by to convert that to 7?
3.5.
7 over 2 or 3.5. Exactly. But of course, you can't leave this like this because you want the coefficients to be integers, right? So what do you do to convert the 7 over 2 into an integer? Multiply the entire equation by 2. So you're going to end up with 2C2H6 plus 7O2 to give 4CO2 plus 6H2O, and that should be the final answer for CO2. Let me just do a quick check to make sure. 714, 8 and 640. Yep. So that would be the final answer. All right. Okay. So balancing equations is very important because that's important when it comes to doing stoichiometric problems. Now, stoichiometry, I don't know if I define what that term means. It's basically a term which describes the type of quantitative relationships that exist between substances involved in a chemical reaction. Balancing an equation is very important in order for us to solve stoichiometric type problems, because that equation that is balanced gives you the proportional relationships between the substances involved in the reaction. So as you can see here in this example, in this simple example where you have this equation right here, you have a 1 as a coefficient for carbon monoxide, a 2 for hydrogen and one for methanol, that's what this is. And basically, you can establish mole relationship based on this balance equation between any two substances. So you can have a mole relationship between, let's say, carbon monoxide and hydrogen. And you can represent that as a what we call a conversion factor or a stoichiometric factor, where you can have, as seen here, 1 mole of CO divided by 2 moles of H2, or you can have it the other way around. And it all depends on what you're trying to accomplish in terms of calculation. And you see here and here some other relationships for two substances in each case involved in the reaction. In this case, it's 1 mole of carbon monoxide exists in a 1-to-1 ratio with methanol, based again on the coefficients in the balance equation. And in this case, this is the mole ratio between hydrogen and methanol, again, based on the mole ratio established by the balance equation. So balancing the equation is important because in so doing, you'll get the correct mole ratio, which you're going to use in whatever calculations you're asked to perform. If the equation is not balanced, then you run the risk of your final answer being incorrect when you do these types of calculations. So basically, when it comes to solving stoichiometric problem, it comes down to this really, right? The relationship between the moles of one substance, which you may be given, or you may have information to calculate that, and then you use the mole ratio, multiply that mole by the correct mole ratio to get the moles of the other substance. And then, depending on how the question is worded, you could be asked to determine something else based on the moles of substance B, right? Or you could be given information that you'd have to use to determine the moles of substance A. So the question that you may encounter can come in different ways. Okay, so here's a simple example. It says when 0.105 moles of propane, which is C3H8, is burned in excess of oxygen, how many moles of oxygen are consumed? And it gives you the balance equation. In some cases, you may be asked to determine the balance equation, but in this case, they did that for us. So what I would do is start off with the moles of propane. And then I would multiply by the appropriate conversion factor. Now remember, the aim of this exercise is to get the moles of oxygen. So what I would do is look at the mole ratio between the oxygen and the propane, which has a 1 here. So I'm going to put 1 mole of C3H8 down here, and then 5 moles of O2 above, and that's it. So according to my calculation, this works out to be equal to 0.525 moles of O2. So this is a pretty simple example of the importance of having a balanced equation and then doing your stoichiometric calculation based on that balanced equation. Okay. So this is an outline of how you go about solving a stoichiometric problem. You may be given, in this case, they're talking about given grams of one substance. You may be given other information as well, which will allow you to determine the grams of that substance A. You convert it to moles by dividing by the molar mass, and then you look at the mole ratio between A and B. Basically, you multiply the moles of A by that mole ratio to get the moles of B, and then, again, depending on how the question is worded, you could be asked to determine the grams of B, in which case you multiply by the molar mass of B, and again, depending on how the question is worded, you may be asked to determine other things based on the grams of substance B, right? So basically, this is pretty much what you need to do in order to solve a stoichiometric type problem, right? I'm just going to put this here. Okay, so some more examples. I'm definitely going to need some space. All right, so let me copy. And paste it. So the question says, the final step in the production of nitric acid involves the reaction of nitrogen dioxide with water. Nitrogen monoxide is also produced. So the question is asking, how many grams of nitric acid are produced for every 100.0 grams of nitrogen dioxide that reacts? So what will be the very first thing you're gonna do in order to solve this problem?
Right at the equation bounds.
You need to determine what the equation is, right? So I want you to look at how the question is worded. And I want you to tell me, firstly, what are the reactants and then what are the products? So let's start off with reactants. Based on how the question is worded, what are the reactants involved in this reaction? I'm sorry? Okay, so H2O and NO2. Okay, and what are the products of this reaction?
Nitric acid, nitrogen.
Exactly. All right, very good. And then what's the next step? You have to balance it. So how would you go about balancing this equation? Okay, go to here. Why two, put it in two? Because you have one nitrogen here. You have two nitrogen plus 1, 3. So I will put a 3 here, right? Okay, anything else? What about the oxygen? The oxygens are balanced? 1 plus 6, 7, 2, 3. Okay, so everything is balanced, right? So this would be the balance equation. Okay, so now that we have the balance equation, what's the next step? What do you think the next step is? Start with the 100 grams of NO2, right? Then what? Okay, so we're gonna have 1 mole of NO2 above, and the molar mass of NO2 would be 14.41 plus 2 oxygen, so that's 32. So according to my calculations, the molar mass of NO2 is 46.01 grams. Okay, so this is going to cancel out with that. Okay, so what do you think the next conversion factor is? Sorry, repeat that.
Nitric acid.
Oh,
Nitrogen dioxide.
okay, so you're talking about the mole ratio, right? So you're gonna have 2 moles of HNO3 as the numerator, and the 3 moles of NO2 as the denominator. Excuse me. What next? Right, so in other words, we're gonna need the molar mass of nitric acid. Let me do a quick calculation on that. 3 times 16 plus 14.01 plus 1.008. So according to my calculation, the molar mass of nitric acid is 63.02 grams of HNO3. And that's it. Oops. This will go with that. This will go with that. So your final answer will be grams, will be in grams of HNO3. So let's see what that gives. 100 divided by 46.01 times 2 divided by 3 times 63.02. So according to my calculations, this works out equal to 91.3 grams of nitric acid. All right. So this is a typical stoichiometric type problem that you can encounter. All right. Again, let me underscore the importance of starting off with a balanced equation, right? If the equation is not balanced, then it's very likely that your subsequent calculations will be erroneous. All right, so make sure you start off with that first. In fact, if you're given a question with an equation, check to make sure it's balanced, right? Just to make sure that you know everything is on the up and up as far as that is concerned. Okay. Any questions about this? Any questions? Any questions? All right. Go back to the PowerPoint to get the other question. So let me oops. All right, so this question says, ammonium sulfate, a common fertilizer used by gardeners, is produced commercially by passing gaseous ammonia into an aqueous solution that is 65% sulfuric acid by mass and has a density of 1.55 grams per mils. How many milliliters of this sulfuric acid solution are required to convert 1.00 kilograms of ammonia to ammonium sulfate? All right, so again, the first thing you do is what? So what would be the reactants in this equation, in this reaction? Based on the information provided in the question.
The ammonia into the, sulfuric acid.
Okay, so ammonia plus H2SO4. And the product will be what?
Ammonium sulfate.
NH4 to SO4. So how do we balance this? How do we balance this? That's it, that's all you need, all right? Okay, so now that we have a balanced equation, let's look at the numbers that we have to deal with now. So the question gives you percentage of sulfuric acid, it gives you the density, and it's asking how many mils of the sulfuric acid solution are required to convert 1.00 kilograms of ammonia to ammonium sulfate. So what I'm gonna do is I'm gonna start off with the 1.00 kilograms of the NH3. And first convert that to grams, right? So that would mean that I would have 1 kilograms of ammonia down here, and 1,000 grams of ammonia above. So that this goes with that. The next step is I would convert the I would convert the grams of ammonia to moles, right? So that means that I'm gonna have 1 mole of ammonia above and a molar mass below, which will be 14.01, 14.01 plus 3 times 1.008, and that would equal to 17.03 grams of ammonia. So that this goes with this. The next conversion factor would be the mole ratio between the ammonia and the sulfuric acid. So that's a 2-to-1 ratio, right? So the way I represent that here is that I'll put 2 moles of ammonia down here as a numerator and 1 mole.
That's denominator.
I mean denominator, I'm sorry. I'm mixing up the math terms. And 1 mole of sulfuric acid above as the numerator, all right? So that goes with that. So far we have the moles of sulfuric acid, but what the question is asking for ultimately is the volume in mils of the sulfuric acid solution. So how do we do that? Well, we have to use these 2 pieces of information right here, the percentage of sulfuric acid and the density, all right? So let's look at, okay. Oh, percent by mass. Okay, so there's one more thing I need to do before we use that. And that is I need to convert the moles of sulfuric acid to grams of sulfuric acid. So I'm going to put 1 mole of H2SO4 down here. And then the molar mass of sulfuric acid. So that's 16 times 4 plus sulfur is 32.07 if I'm not mistaken. Yep. 32.07 plus 2 times 1.008 for hydrogen. Okay, so for the sulfuric acid, I got 98.09. 98.09 grams of sulfuric acid. All right. So Okay, so here's where we get from the acid itself, the pure acid itself, to the solution. The 65% sulfuric acid by mass. What that tells us is that for every 100 gram of solution, there is 65 grams of sulfuric acid. And the way I represent that here is that I'll put 100 grams of the solution. And down here, I'll put 65 grams of H2SO4. All right, so that this unit, grams of sulfuric acid, will cancel out there and there, right? So that's 100 grams of the solution, but we're not finished yet because we need to find the volume. So we have the mass of the solution so far. To get the volume, we need a density. So I'm just going to continue the series of conversion factors down here. So how do we represent the density here? We're going to put 1.55 grams of the solution here. And above, you're going to put 1 mil of the solution. And that's it. This is going to cancel out with that. And that's basically the setup. So let's see what this gives. 1 times 1,000 divided by 17.03 divided by 2 times 98.09 times 100 divided by 65 divided by 1.55. And according to my calculations, when rounded up to 366, the answer becomes 2860 milliliters of solution. And that's how you do that. All right. Any question about this one? Any questions? Any questions? Questions? Okay, can I get back to the PowerPoint? All right, so. Do we have time to discuss this? Okay, let me at least get this started. I'm going to go through it again quickly because again, this is something that you should have done before. This whole concept of limiting reactants. Now, sometimes, in fact, more often than not, whenever you're trying to perform a chemical reaction based on what you know what the equation is, you might want to, well, you might try to make sure that the measurements are careful and accurate such that the amounts of reactants are stoichiometrically equivalent. However, in practice, what you'll find is that in most of those cases where you do that, the reaction does not go to completion. In other words, not all the reactants are used up. So basically what you'd have to do in order to ensure that the reaction is driven to form products, you have to make sure that one or more of the reactants will be in an excess amount beyond what is stoichiometrically required, right? So basically in those kind of situations, what you'll find is that there are two types of reactants involved in such reactants. You have what is called a limiting reactant and the excess reactant, right? The limiting reactant is basically the reactant that is completely used up in a reaction. And the reason why it's called a limiting reactant is because it is also the reactant that determines how much of the product you expect to get. So it limits the amount of product that one is expecting from the reaction, right? Key thing you need to remember here, and you probably should know this from your previous experience, the limiting reactant is not necessarily the one in lesser amount because it also depends on the stoichiometry of the reaction, the coefficients of the different reactants in the balance equation. So to illustrate this concept of limiting reactant, we're going to use a non-chemistry example. So let's say you're given a task of preparing a packaged meal according to this formula, right? You have 1 sandwich, 2 cookies, and 1 orange, and that combination gives you 1 packaged meal, right? So I could write this in the form of an equation. A sandwich, I'm going to use SA to represent a sandwich. For cookie, I'm going to say CK, and you need 2 of those. And then for the orange, OR, and that will give 1 package meal, right? So let's say that's the equation you use for describing what we're doing here, right? Okay, so let's look at this situation. Let's say we have, or you're given 10 sandwiches, 18 cookies, and 12 oranges. So the question is, how many packaged meals can you make out of this combination, right? Now, if you look at things from the standpoint of the sandwiches, right? According to this equation, or according to this guideline right here, if you have 10 sandwiches, right? The amount of cookies you're going to need would be 20 cookies, right? But you don't have 20 cookies, you have only 18, right? So basically, there's a mismatch right there in terms of the equation. If you look at things from the standpoint of oranges, right? If you have 12 oranges, that means you're gonna need 24 cookies, but again, we only have 18 cookies, right? So basically, the cookies will be used up, but you're gonna have some oranges and sandwiches left over, right? So it turns out that the cookies will be the limiting item, because for every 2 cookies, you're gonna need 1 sandwich and 1 orange. So if you have 18 cookies, how many sandwiches you're gonna need to use up all those cookies? If you have 18, you're gonna need 9 sandwiches, which means that you haven't more than enough sandwiches, which means that you're gonna have 1 sandwich left over. And then as far as the oranges are concerned, you're gonna need 10 oranges, you have 12 here. So therefore, the oranges would be not used up as well. So basically, sorry. So basically, we can set up a table which looks something like this. Originally, you have 10 sandwiches, 18 cookies, and 12 oranges, right? So basically, for every 18 cookies, I think I misspoke. I think you need 5 sandwiches, right? Because for all the 18 cookies used up, you're going to use up 5 sandwiches, leaving behind 5. For the oranges, actually you're gonna need 7 left over for the oranges, all right? So the point I'm getting at here is that you're going to have some excess items left over, while all the cookies would be used up. So therefore, in this particular context, the cookies would be the limiting item, right? While the oranges would be in excess, and the sandwiches would be in excess as well. And because the cookies would be limiting, that's an item that would determine how many packaged meals. So in terms of the number of packaged meals that you expect to get from this, hold on.
I think you messed up there.
Yeah, I messed up
You
real
you have
bad. Okay,
9
I'm sorry.
9 sandwiches. Right?
Yes.
Yeah, there should be 9 sandwiches. So I was right the first time. I don't know why.
You had 3 oranges left over.
So this should be 9 sandwiches. So 1 would be left over here, would be 9 oranges, so you're gonna have 3. I'm sorry about that. Yeah, so you're gonna have 1 sandwich left over and 3 oranges left over, no cookies left over. So again, still remains that the oranges and the sandwiches will be the excess items. And therefore, as a result, the limiting item, which is the cookie, will determine how much of the meals that you're gonna end up with. If it's 18 cookies, that means that you're gonna end up with 9 meals. All right, so that's basically how we'd apply the limiting reactant to a situation like this. But we can also, of course, apply it to actual chemical examples, such as this reaction here between 2 compounds. One of them is ethylene, which has this formula, C2H4, and it's going to react with bromine to form C2H4Br2, all right? So this is a very simple reaction because of the 1-to-1-to-1 ratio between the different items, right? So in this particular example, they're starting off with 28 grams of ethylene, and it's reacting with 120 grams of bromine. In terms of moles, this is 1 and this is 0.8, all right? So obviously in a 1-to-1 situation, the item that is in excess would be the ethylene, right? So what will happen is, let's see here. Okay, I don't have the space to scribble, but basically because it's a 1-to-1 ratio, between the two, what will happen is that the bromine being the limiting reactant will react with the same amount of ethylene, which is 0.8. So therefore, the amount of ethylene left over would be 0.2 moles, right? So as a result of that, so that answers this question here. What mass of ethylene is left over? And the answer here is 0.2 moles, all right? And then in terms of the product itself, the amount of product you expect to get will be 0.8 because the bromine is the limiting reactant. Of course, you'd have to convert that to grams to get a mass. And according to the information here, the amount of the product you're going to end up with is 150 grams of the product, which is 1,2-dibromoethane. In addition to that, you're going to have the leftover ethylene, which is 0.2 moles. All right. So that's another example of the limiting reactant concept. All right. Okay, let me leave you with this. So when it comes to solving problems involving limiting reactants, basically you have to determine which reactant is the limiting reactant. And basically the best way to do that is to solve with doing stoichiometric calculations. I think there's an example I have. Yeah, okay, so next class, I'm going to get into this example right here to show you how that works. All right, so I'll just leave it at that. Before you leave, let me remind you of the event next Wednesday. If you can't make it to the Ocala campus, I will provide a Zoom link for you to join up. I'm thinking of giving you guys extra credit for attending. I'm decided in what form that will take yet, so I'll let you know. All right. So look out for that. I'll post it later on today. All right, Zoom link. All right. Okay, folks, that's it for today, folks. Yes, sir.
Say the event was.
12:30 on Wednesday. Right. And then if you're going to be at the Ocala campus, it's going to be in building 3 in that common area.
When is all the subject reading?
Well, we're not finished with it yet. In fact, I'm glad you asked that question because based on what we have covered, let me see. Based on what we have just covered. Primary 3. Okay, so now you should be able to do questions 3, 4, 5, 6, 7, 8, 9, 10, and that's it. So questions 3 through 10. All right, so work on those. If you have any problems, please let me know. Oh, okay. Mhm. That looks right.
I need to get them in.
Okay, then. Let me draw this out to 260. So I need another digit here. And then I
It's just. It's just because it's like.
first, oh.
Yeah.
I could, which is so much about I can get rid of. You wrote today?
You know what, you can make things more complicated because what I would have done, the question says.
It's not
The
like,
question says it contains only carbon and hydrogen.
Yeah.
Right? So basically, you could have just stopped right here. Instead of multiplying by these two, and you get the moles. Right, which would be this, which should be the same as this. No. The only reason why you convert the grams is if, like, for example, there was an oxygen present, in which case you needed the masses of both carbon and hydrogen, that you'd have to subtract from the total mass to get the mass of oxygen.
So if there was oxygen.
Right, then you do this, and then to get the mass of oxygen, you add these two together and subtract it from the mass of oxygen. I'm sorry, subtract it from the mass of the original compound. And that would give the mass of oxygen, right? So it was, yeah, if it's a hydrocarbon, then you did not need to, well, let me see what you have here. 0.00586 divided by 44.01, and that's it for that, and then. And I think another problem too is that you roll it out to earth, so it should be a 2 here. And then for this, it's 3.00137 divided by, oh, and here's the other mistake. Remember what I said about, or maybe, I don't know if you were here, but I was saying that, for every 1 mole of water, there are 2 moles of hydrogen. I don't know if you were here, but I was telling everybody that, that's a common error that students tend to make, so let me see here. Divided by 18.02 times 2, so that gives you, so this here should be, 1.5 times 10 to the minus 4. So when you divide 0.00132 by 1.52 times 10 to the minus 4, 8.6. Try to see. So this done, this will not be the empirical formula, this will not be the empirical, it will be, it would be a 1 to 1.14 ratio, right? So we have to do some trial and error to see what we can multiply this by to convert it into an integer. So I'm just going to try 1.14 multiplied by, let's see. Oh, hooked up. So if I multiply this by 7, I'm going to get 7.98 and multiply this by 7. So the final answer would be, so this is approximately 8. So the final answer for the empirical formula is going to be C7H8. That's it. Right? What's up?
is there any way I can still turn in assignments if, or have you already posted the answer?
You can email it to me,
Okay, just put the PDF documents in.
you can email it as an attachment.
Okay, thank you.
All right.
I was just gonna ask if you saw it.
Oh, yes, and I replied, I don't know if you saw the reply. I have it. Well, because I asked if you know where or who I should submit it to. Here it is.
Pretty sure just,
Alright, so, okay, so you take it to the advisor.
I'll take it right now.
Okay, all right, no problem. Yeah, no problem.